Right, good afternoon. What I'm going to talk about is refactoring to immutability. And I'm specifically bringing these two words together because there's no shortage of sessions that will urge you how wonderful making things less mutable is, so I will clearly start with that. The problem that most people encounter, though, is that they already have stuff. And it turns out that that stuff, the only way it's immutable is the sheer fear of having to change it. Okay? The wrong kind of immutability. And it is filled with mutability. That becomes the problem. So there's a kind of a from here to there. How do we do that? How do we reason about it? So there's a little more of a cookbook element to this in the sense of trying to make things possible. Because it's all very well people coming along going, oh, there's this beautiful land. We can reach it. Or, you know, if you're there, you're there. But everybody else is here. How do we get there? That's what I'm going to talk about. My name's Kevlin Henney. I do various bits and pieces. I talk about some of this stuff in one form or another. And I have a very strong interest in code, the way people express themselves in code, the challenges that they find there. And I quite like words. I think words are lovely things. And I love wordplay. This is one of my favorite titles. It was from Communications of the ACM a couple of years ago. Immutability changes everything. I love that. Just as we have this challenge of refactoring to immutability, it's just there's this notion of we're constantly dabbling in change and not change. Now, for many people, when they think about immutability, these days, they tend to think about functional programming, which I think is kind of sweet. Welcome to the club, everybody. Nice of you to join us with the idea of immutability that's kind of been no, it's quite old. It's a very mathematical concept based on Platonic solids, basically. There's a sort of an immutable truth out there beyond our universe. Functional programming is kind of it joined the game late in the 1950s. So all those people are really getting into 1950s programming. Well done. But there is a nice way of thinking about this that Michael Feathers tweeted a few years ago. And I think his rationalization, funnily enough, it was the way that I explained this to a colleague many years ago, yet without the brevity of old school tweeting. It's this idea of we are constantly focused on how do we organize state? How do we get our heads around this stuff? And each discipline, each paradigm that comes along offers us a new way of reasoning about the relationships between behavior and state. And it does so in a way that ultimately we can fit it inside our heads. And we use various excuses like better hardware and so on to justify this. But ultimately it's about what can we do. OO makes code understandable. The operative word here is not executable but understandable. It's about you. Hence the challenge or the desire to refactor. It's ultimately about you. It turns out the processor doesn't really have a strong interest or a strong care about this stuff. Makes code understandable by encapsulating moving parts, which I thought was a lovely way of putting it. What we're doing here is, rather than having kind of spaghetti state management, what we're going to do is we're going to organize things ravioli style. And we're going to bring things together and say, sure, there's some state change, but it happens behind closed doors, and we can reason about it clearly through a method boundary. But it is isolated. It's the notion of isolation that allows you to reason about it. Functional programming makes code understandable by minimizing moving parts. Notice that these two desires are ultimately about you and your ability to reason about things. But I like that idea of, here's a different road. We're going to reduce the number of moving parts that we have. If you've got a turntable, given that vinyl is coming back into fashion, if you've got a turntable, I used to have an old dual deck, and you pay so much more for a turntable that has fewer moving parts. Because why is that? You know, it's just, there's none of this auto-tracking, press a button, things happen. Oh no, you have to move the needle into the position, and you pay for the privilege. Okay? But what you get is reliability. There are fewer moving parts, therefore there is less that can break. And it's exactly that kind of reasoning. So, you know, there are other things that people value about functional programming. Why do you like functional programming so much? What does it actually get you? I just love that. Tail recursion is its own reward. I think it's just that it says everything. If you don't find that funny, then I would go to one of the functional programming sessions. Functional programming combines the flexibility and power of abstract mathematics with the intuitive clarity of abstract mathematics, is another way of looking at it. However, the bit that concerns us is functional programming typically avoids using mutable state. And that is, I think that's a very moderate statement, actually, because given that it comes from the Haskell website, because Haskellians would normally say it completely avoids, but they realize they need to speak to people, and they, so therefore they've compromised, typically. I like that, yeah? So let us start with a very simple observation from Bertram Meyer, who wrote the book Object-Oriented Software Construction many moons ago. Asking a question should not change the answer. This is philosophically interesting and valid, but clearly he doesn't have children. But nonetheless, it gives us a starting point. Asking a question should not change the answer. So that means if I can frame my code as a series of questions, asking things about other things, then we can have a very nice property. It is the idea that that thing that you left, you walk away, you come back to it, it is still there. Okay, there's no surprises. The principle of least astonishment. More importantly, and likewise no children here, and nor should asking it twice. Idempotence, which is one of those glorious words that means nothing unless you know the Latin. Idem meaning same, potens meaning force. It has the same force no matter how many times, the same effect every single time you call it. So there is this idea we can rely on an expression having not just a particular intention, but actually having a particular value. And we can repeat that. There's less to worry about. So a number of years ago, I edited this book, 97 Things Every Programmer Should Know. And that was around 2010. And what is nice is that there's about 2 or 3 items in there that, as it were ahead of the current trend for functional programming that were really sort of urging you, start thinking like this. It's valuable. Ed Garson, in Apply Functional Programming Principles, makes a point about referential transparency. A very desirable property implies that functions consistently yield the same results given the same input, irrespective of where and when they are invoked. This function evaluation depends less, ideally not at all, on the side effect of mutable state. So ultimately what we're after here is a very simple desire. Now, this is not exactly a groundbreaking statement. Your code should be reasonable. Yeah? It might even be understated because, I mean, we often talk about your code should be good, it should be clean, it should be awesome. I'm just saying it should be reasonable, which sounds like a complete lack of ambition, except that I want to draw your attention to the fact that the word reasonable has more than one meaning. Okay? You should be able to reason about your code. Your code should be both reasonable and reasonable. Okay? You should have the capacity, the ability to easily grasp it and understand it, load it into your head, and be unsurprised by the outcome. So, what stands in our way? John Carmack, games programmer extraordinaire, made this observation in a functional programming in C++ article a few years ago. A large fraction of the flaws in software development are due to programmers not fully understanding all the possible states their code may execute in. And I think this is quite important because what we end up with is sort of a failure to understand the consequences of the simplest choices in our code. Does anybody know where this comes from? Yeah, war games, excellent. If you don't know what war games is, you have between now and the film release of Ready Player One to figure it out, because otherwise you won't get anything, yeah? Okay, so I grew up in the 1980s, and this is what we worried about, nuclear war, so hey, no change. I'm really glad that my kids can get the same kind of experience of like the threat. It's just like, hey, sons, this is what it means. Imminent apocalypse. The world is on the edge here. So it turns out I have watched this with my older son. The minute it was about 2 or 3 years ago, and it was so funny after we watched it. He said, "Dad, can we program an AI?" And it's just like, okay, that's a little ambitious, but let's just start with some Python here. So how to get kids into programming. I want to create a malevolent, amoral AI. So the reason I introduced this here, because things can get out of control very rapidly. you end up with global state problems. You can end up with global thermonuclear war. And the observation that John Carmack makes furthermore, and this is another concern that people have suddenly discovered they have, in a multi-threaded environment, the lack of understanding and the resulting problems are greatly amplified, almost to the point of panic if you are paying attention. Now, I love that sentence, if you are paying attention. If you are not panicking, and everybody else around you is somewhat concerned, you have missed something. You're either in a very happy place and it all works for you, or you have missed something. Now, I'm not a gambling man, but I'm going to put my money on you missed something, okay? If you are paying attention. So, as I said, I was a child of the 80s. There was a, does anybody, let me just context here. Threads, did anybody see that? So yeah, just a handful. You have to be of a particular age and have to have grown up in the UK and been of a televiewing age, appropriate age. This was horrific. This was a TV, a docudrama about a bomb drop over Sheffield, an airburst over Sheffield. It was utterly horrific. It came the year after an American film about nuclear war. It's called The Day After. It made nuclear war look quite moderately pleasant. It was sort of like sort of Dallas or Dynasty with bombs. This one pulled no punches. It was utterly, utterly horrifying. I remember going into school the next day and we just sat there kind of like slack jaws, like, wow, that is scary stuff. But the program was called Threads. That's what I want to put in your mind. Okay? Threads. This is how you think about threads. Okay? This is what you need to be thinking. Ultimately, atomic war or lack of atomic war. Normally what happens with this is when people think threads, what they think of is locks. There's a kind of a built-in association in many people's minds. You say threads, they say locks. Okay? And what they're doing is, why do we have this association? People often say, well, I want to use locks for safety. Okay? It's like, well, wait a minute, let's pause a moment. Why is your code unsafe? What line of reasoning caused you to create code that is unsafe? So I drew up, during a workshop a few years ago, I drew up the simple quadrant diagram, and given that it's the afternoon and your brains have gone into carbo slump, this is about as far as we're going to go here. This is all we need, a quadrant diagram. It's nice and easy to reason about. And basically, we can divide up the relationship between behavior and state in your program very, very easily. Your state can be shared between threads simultaneously, or it can be unshared. Okay? That state can be mutable or immutable. Now, that gives us a rather interesting diagram here of where we actually need to lock stuff. Also, let's just make this really clear. As with any quadrant diagram, normally one quadrant is very, very good or one quadrant is very, very bad. In this case, it's very, very bad. Okay? And just so there's no doubt, I've used the universal color for danger here. This is red. And, in some cultures, red is the color of celebration. That's the consultants. And this is the synchronization quadrant. I want to point out that 1/4 of the diagram is bad. The other 3/4, all is good, and life is simple. Because if you are not sharing data, you can do what you want with it. If this thread has this data and nobody else ever gets to see it, then we're good. Or if they get to see it, it's only after it is handed off explicitly. In other words, it's only one thread at a time. We have unique and exclusive ownership. You can make it mutable, you can make it immutable. The point is that no change will be visible to anybody else. Alternatively, you make everything unchangeable, immutable. Therefore, you can share with impunity, and that's great. You don't need to do any locking. Now, there may be locking. When I say you, I mean you as a developer. You don't need to take this stuff into account. If you are using queues to hand off relationships from one place to another, then clearly there will be locks at some level. But I'm saying those are commoditized locks. That's not something you as a developer have to be concerned about. Or put it another way, you are not given the privilege or the ability to get it wrong. Okay? You are not given that degree of freedom. You hand something off to a queue, and it's just like, no, queue, I'm going to mess with your locking strategies. You don't get that option. So this is the curious thing. Why do we end up with, we seem to be like moths drawn to the flame of the top right-hand corner. How do we end up with all our code in the red zone, in the synchronization quadrant, the quadrant where we are most likely to make the errors, most likely to struggle with our reasoning, and also the area most likely to slow down your code? It is always remembering that the point of a lock is to stop concurrency. Yeah? As I noticed on the walk here, admiring the traffic, because Westminster Bridge has been closed. So there is a point. How do we end up in this quadrant? Why is all the reasoning in our languages gravitated towards that? Why is it reflected in our languages? So once upon a time, we did not have all this stuff. So let's just pick on C for a moment. Okay? C does not have any primitive constructs for threading. So basically all APIs ultimately end up in C. And the constructs like locks, mutexes, to acquire and release, those are built into libraries. And so then we have Java coming along in the mid-90s saying, you know what, we can have a built-in statement, a synchronized block, and then C# reflected that with its lock block. So these were initially seen as an improvement. We have the ability to synchronize built into the language, along with if statements. But if we pause for a moment, we realize it's actually a step backwards, or rather a step in the wrong direction. We've commoditized the wrong thing. Because what we've ended up with is an encouragement that, hey, locks are easy. You can stop your program really easily. You can slow it down. That's what these constructs are for. They are the elimination of concurrency. So historically, there is actually a very simple answer. Let's go back to C. Once upon a time, all your code was naturally on the left-hand side, because you couldn't share between threads because you didn't have threads. That was easy. Yeah? So all the code gravitated to the left-hand side. And for reasons of history, in other words, programming languages growing out of an imperative model assembler, as well as resource constraints. And I know people are always complaining about resource constraints, and I did have somebody complain about some of the techniques I was proposing for a particular project. It was a couple of years ago, and he said, yeah, I don't know if we can do this on our project because it's embedded, and we may not have the memory resources. And I said what kind of memory resources are we talking here? What kind of constraint? What kind of hardship are you working under? And he said 128 megabytes. And I said, get back to me when you have a problem. Yeah? At this point, I'm going to start saying, when I was a lad, you're lucky if you got 2 bits to rub together. Ones and zeros? No, we didn't get both. Yeah? So the point here is that naturally drew all the code into the top left-hand side. When threading became commoditized, it just opened up this new territory on the right-hand side, so we naturally wandered over. Hey, look, we've got procedural thinking. Let's just add threads to it. And excitement followed. So let's talk about the idea that this is architectural. It's not merely a language construct. Architecture represents the significant design decisions that shape a system, where significant is measured by cost of change. It turns out taking a code base that has an assumption of I can change anything and turning it into a code base where that's not the case is non-trivial. It's not just simply a case of create new code in an immutable style. There is a genuine challenge here. And the appreciation, it's not a new appreciation. The term technical debt dates to 1992. That was Ward Cunningham. Meyer Lehman wrote this in 1980. As an evolving program is continually changed, its complexity, reflecting deteriorating structure, increases unless work is done to maintain or reduce it. So what we're dealing with is the problem that somebody said immutability is really nice, but what we have here is a legacy system. We have the past. Being an incurable romantic, I took my wife and kids to Stonehenge last year on Valentine's Day. Why wouldn't you? I took this shot, and the kids were impressed by the size of these monoliths. Monolithus coming from the monolith comes from the Greek, monolithus meaning one stone. Big stone, hard to move stone. So, it makes that experience of your legacy system feel real. You can't move these easily. Or you're wondering how people move them at all. And this becomes the challenge. So when somebody comes along and says, you need to refactor, we look at this and we say a change made to the internal structure of software to make it easier to understand and cheaper to modify without changing its observable behavior. How much change is that? To change something that naturally assumes everything is changeable into something that is more local, based on data flow and immutable objects is non-trivial. So some of these may end up being big refactorings. So what we're going to focus on here is the developmental side. You can kind of look at any software system and break it along roughly. It's an approximate right-hand rule. Given that my fingers are not at right angles, I don't have any problem saying that these axes are not perfectly at right angles either. But we can break it down: functional behavior, operational behavior, execution, use of resources, performance, all this kind of stuff, and developmental qualities. Refactoring concerns itself with the developmental dimension. In other words, you keep the functional behavior the same, you preserve the semantic behavior. When you refactor, that is preserved, developmental quality hopefully improves, and the operational can go one way or the other. If you're optimizing something, the goal is slightly different. You keep the functionality the same, you improve some aspect of performance, but the developmental quality may suffer. So this is kind of an important idea, the preservation of functionality and functional behavior. There's no good having an optimization that breaks. So I'm looking at you, Spectre and Meltdown. People are saying, oh, that's hardware fault. No, it's actually a software fault. Hardware is software, okay, the way that those are structured. So how do we do this? We have a bit of a problem, because it's not that when you walk away, you don't have knowledge of a number of techniques and functional ideas or immutable techniques for your objects. The problem comes that you may find yourself working uphill or working against the grain. As observed here, many programming languages support programming in both functional and imperative style, but the syntax and facilities of a language are typically optimized for only one of these styles. And this is the most important bit. Social factors like coding conventions and libraries often force the programmer towards one of the styles. So it turns out programming is a very cultural thing, and many of the cases where I've seen coding problems in existing legacy systems, it is not because people have been stupid or evil. It is simply because the code, as much as they want to go that way, the code wants to go this way. All of the libraries, all of the conventions say, no, you need a default constructor here. No, you need to expose these as public. No, you need to do this. To go against it is to basically have a system that does not build, which on the other hand is not bad, because then you don't have any bugs, and people can't complain about bugs in production. It's just you have no production. People might complain about that instead. So there's a challenge here. That said, people do often have various habits, not all of which are healthy. Looking at you, Singleton. So that's my Singleton. That's actually quite a good Singleton. It's far better than the kind of Singletons people put in their code. But people get into this habit of putting this stuff in. So let's deal with this kind of idea. Let's imagine that we have some kind of clock concept. We're going to have an instance. We're going to make it global. So we've got clock.instance. There's a singleton there. And from that, we can get the time of day now. And that's great. So everybody universally accesses the clock. And there's only one true clock in the system. OK, what's the example code look like? Well, it looks a bit like that, which is... Has anybody come across the law of Demeter? Law of Demeter? OK, not a lot of people. It's a slightly obscurely named thing. It's nothing to do with Demeter, who's a figure in classical mythology. It's actually to do with a software system that was developed, a research system developed in the 1980s. And the system was called Demeter. And Carl Liebherr and others observed that there was a practice that they had adopted, which is basically don't create, well, we would now call it as basically don't create method chains or train wrecks. Don't end up with stuff that goes thing dot thing dot thing dot thing. We're not talking about fluent APIs here. We're talking about digging into an object structure. I'm going to get you, then I'm going to dig into something else, then I'm going to dig into something else, and then somewhere at the bottom is the value that I'm after. Problem with that is there is an immense amount of coupling through the intermediate object structure. And it's a little bit like long URLs with too many components. Their eyes start glazing. They very rarely reach the end of the train wreck. It turns out that any use of singleton automatically is a violation of the law of Demeter. So that's just a minor observation. So that's what our code looks like now. And so we have the simple question that people often have. Well, you know, why should I replace the singleton? It makes my code convenient. Look, that's how I get the time of day. Yeah, you know, it's really easy. Now, you have a bit of a problem. First of all, I've got I'm going to put really good money on the fact that although I've got 3 time devices, I've got one of these, I've got a phone, and I've got a laptop. I'm prepared to put money on the fact they do not tell the same time. It turns out that clocks have different times. I have worked on an embedded system where we actually had 2 different clocks, and you had a choice of where you got your time from. It was to do with granularity and purpose of the clock. So first of all, we said there is only one universal clock. Now, that may be true for your system. But we do have another interesting question. How am I going to test this? How am I going to unit test this? I can't unit test it. Oh, that's fine. Run it as administrator and change the time for your unit test. At this point, you will discover that the answer to the question, are we alone, is no, because there are other things running on your machine that may have a strong opinion about you messing about with time. You are not a Time Lord, okay? Oh, well, within a certain constraint you are. But this convenience, what have we done? We haven't actually made anything that much more convenient. We've maybe saved a couple of characters, so let's just change this a little bit. Whoa, that's amazing. How did you do that? Did you actually pass in the clock? What we've done is we've changed the idea of time being a universal, which it isn't. We knew this in 1905, so why it's taken us till 2018 to acknowledge this. Time is not a universal. What we've done is we've passed in a concept of time. Here, you're a piece of code. I want you to use this time. That's it. Or rather, this source of time. Time is a resource, just like a file. I don't want global files. I don't want global database handles. And most things that people think, oh, I can just access time out of thin air, that's a programming convenience I wish did not exist in most APIs. Time, here we have. I'm going to pass you a clock. Use this one. It's that one or this one. Doesn't matter. You don't have to worry about where it comes from. And we now have a very simple concept there. Interface clock. And we can go ahead and have a clock import. Now, if you're a .NET person, you're probably struggling a little bit. You can't read the first line. You're going like, geez, what's he done there that I can't read? Oh, he's missed out the letter I. That's what he's done. Oh, I knew I couldn't read it because it doesn't have that weird wart that I put all over my code. And yeah, those people who do the impl thing, God, they're so stupid. No, if we do iClock, then we can use clock. It's the same problem. Okay, it's the same problem. What you've done here as well is we can clarify as a failure of abstraction. There's a refactoring here. So first of all, we factor out, we move the things that are global to be parameters. The second thing we do is we decouple the parameter from a concrete type. The next thing we do is we accurately describe the concrete type. And unfortunately, both the impl and the I approach have this habit of allowing you to be lazy with names. What you've done is you've accidentally missed the opportunity to name the concept. What kind of clock is that? It's a clock. Wow, thank you for that. It's a local clock. Ah, that's a little more useful. It's a mock clock. It's a whatever clock. Tell me what it is. Okay, you have this. You know, you've got autocomplete. You've got. I mean, I'm not even using up loads of names here. I mean, given that most of your code base probably has abstract controller factory singleton clock, then this is quite a simple economy. Okay, so then we can mess about with whatever naming conventions we like. Okay, so that's the first bit. The next thing is you might realize the only thing you're ever going to get from the clock interface is one thing, the time of day. Well, you can actually narrow the abstraction. You don't need an interface for that. So we don't actually need to introduce an intermediate abstraction if our language, such as C#, such as Java, supports the ability to pass through a simple direct functional abstraction. So yeah, give me the time of day. So now what I've done is I've reduced my source of time to a simple function, and I can simply call it when I need it. And then the most mind-blowing thing is, why don't we just pass in the time? And what we've done is instead of making this a higher order function, we've simply said, example is a function of time. That is actually directly stated. We haven't hidden a dependency. In the original example, we had the idea that there was a hidden dependency. We'd obscured it. We had made something convenient by saving a few characters typing, but we'd actually lost the explicitness of this is time-dependent behavior. Now we've just turned it into a pure function. This is much, much simpler. So one of the things where people are passing around controllers and factories and provisioner-type objects is simply a case of like, well, what's the result that you want? Let the person who calls it make that decision. Okay? This code is far simpler to test, to reason about, and so on. Of course, there is the possibility, as Alan Perlis noted in the early 80s, if you have a procedure with 10 parameters, you probably miss some. So clearly you cannot just keep on abstracting and adding extra arguments. That tells you probably that you've got too much behavior. But it tells you can also group the behavior. OK, so we can see there's a bunch of things. Reducing scope of variables, eliminating second assignment, which I haven't covered, globals as parameters, replacing long parameter lists with parameter objects, which I haven't covered, and replace resource passing with actually give me the value that you want. So let's explore that time of day thing a little bit further. So in this book that I co-authored a few years ago, we talked about the idea of immutable values. Define value object types whose instances are immutable. The internal state of a value object is set at construction and no subsequent modifications are allowed. So the idea is that your object has a value and it retains that value. In many ways, this is unsurprising, but for a lot of people, they don't think about their code in these terms, so they end up naturally shoving in setters. So we can actually take some examples. I have some currency in my wallet, and I have a choice of currency, so I'm going to choose something that's a little more stable than the pound. I'm going to choose the euro. I have no idea what the pound is doing, probably falling, who knows. And what we have here is I've got 20 euros here, and this is 20 euros. It will retain its 20 euro-ness for all of its life. I have another 20 euro here. They differ only in their identity. Well, I make that bold statement. Let's just check they're not. Yep, they do actually have a reference identity. That's a serial number. They are different. So although they have identity, that's not how we use them. Their usage is anchored in the value that they can present. That's all very logical. That's all very nice. And we know that. And we suddenly find ourselves inside an IDE, and boom, before we know it, we've got setters everywhere. Why have you got setters? Because my IDE allows me, it just automatically puts them in. Oh, I've got a really good shortcut. It puts get and set in every single time. Yeah, I can do the wrong thing faster, at speed. Look at this automated bad code generation, yeah? And we fall into this little trap because of an accidental quality of English, that get and set, they rhyme, they share most of the same spelling, they feel like opposites. They're not. To get is to ask a question. Although it's actually a slightly rude way of asking a question, get is a very raw English verb. Get implies side effect, in case you were wondering. This is often a concern, often a surprise to people who come to English via the road of development. It's like, yeah, get means query. No, really it doesn't. Disappointingly, when I got some cash from the machine in the wall, my bank balance went down. Side effect. Okay, you get money, there is a side effect. You get married, there is a side effect. Okay? Yeah, so the word get in English means the following will change the world. It will have a side effect. Okay? So we've been lulled into this kind of convenience because the words have a certain euphony. Oh, yeah, get, set, and we do this. I often have this in classes when I'm running test-driven development classes, where somebody will quite happily be writing good tests, and then I'll say, what's that setter doing? Oh, yeah, it was just there. Yeah, it's just like, no, it wasn't just there because the code didn't exist 10 minutes ago. It didn't just appear. Or rather, it appeared through the power of fingertips. But there's no test that corresponds. So if I delete all the setters, the test will still run. Yes. OK, let's delete all the setters. But don't we need set? Sometimes people feel a little uncomfortable with this kind of loss of perceived symmetry. So let's go back to our time of day concept. OK, we've got hours, we've got minutes. I'll skip seconds. And we've got this idea of I can change the hour, I can change the minute. I presume that there's going to be appropriate bounds checking on that. And I can also ask it, please move to the next hour, please move to the next minute. And many people will arrive at the solution, perhaps without realizing this, and then they'll go and build an implementation like that, which, yep, good, I believe it works. I think I wrote tests. That's fine. OK. So let's go back to this. How are we going to make this immutable without breaking all of our code? Well, the first thing we can do is obviously get rid of the setters. Now, that only does half of it. That's the how do I make this immutable. I'll get to the next bits in a moment. But without breaking our code. Damn. If I've got stuff there that did actually end up relying on those setters, then I've broken the bubble, I've broken the illusion. It's not a good refactoring because it no longer compiles. So I'll just shorten that. So we've actually got hours and minutes. OK. what we're going to do is we're going to recognize that setting is a different way of looking at something. What we're doing when we're setting, instead of saying, I'm going to change the value of this object, we start from a different position. We say, given this object in this particular state, what I would like is an object that reflects the following change. It's a polite request rather than a forceful request. Okay? Please give me an object that, if the time is 15:35, please give me an object that has the hour as 16. Okay, so what I'm doing is I'm asking for a transformation. I'm asking for a diff. And I'm going to say, if you've used a version control system before, you might be familiar with this approach. Okay? So therefore, that's what we're going to do. We're going to change the sets to widths. We're going to say, given this, when I transform it, then give me that. It turns out we are already familiar with this. I don't know, maybe you were 4, maybe you were 5, maybe you were 6. But when you were taught to add numbers, this is how you were taught. The teacher came along and said, OK, you've got 2, and you now add 3. And you get 5. Wow. That's great. And you're able to use the same 2, the same 3, and the same 5 the next day. They haven't changed. The addition of 3 to 5, the addition of 3 to 2 did not change the 2. Okay? There are programming languages where you can do serious violence to the concept of such numbers. We do not recommend that. But what we're doing here is we're saying 2 with an extra 3. That's what we're saying. It's like, oh, that's great. So the problem that I find when many people do that, they say, right, we've got rid of the setters. Yeah, but you haven't, and now you've broken my code. How do I do this without creating too many changes in my code? Well, it's just a simple transformation to a with. We also say next hour. So the next hour is now a query, although you may want to go via a renaming to avoid some of the surprises, because it turns out a point of call, these both look identical, or can look identical, and you may discover that this is not going to work out for you very well. It's like, why is my code not working? I've still got calls to next hour. So there is a scope for making it actually actively incompatible and then reverting to the most convenient name. So we can do this. Let's put in a constructor so that we can actually see that we start off. So the most important thing is you give an object a good start in life. And one of the things we're going to say is actually in many cases with value objects, we don't support the idea of default construction. Now, this is a problem. I just want to clarify. When I'm using the term value objects, I'm using it correctly, unlike .NET, which means pass-by-copy objects. It turns out that string is a value object that's not a value object, which is confusing in vocabulary. So when I'm talking about values, I mean things that model values, like currency, like time of day, and so on, not the struct types. OK. You want to make, if with is not enough for you, you can add in a builder. So think string, string builder. So you can go through progressive changes. So we've now got the code. It's about the same amount on the slide. We haven't actually changed the amount of code. At usage, it's about the same amount. So this is the interesting thing, is that we've ended up with the same amount of code, just phrased differently. This is a relatively simple thing to do. Will your object creation costs go up or down? Yes. It depends how you're using it. It turns out if we're sharing this, then that means I don't have to do defensive copying. There's a lot of code that has defensive copying. I'm going to give you a copy of this because I don't know what you're going to do it. Or, alternatively, it has defensive comments. Hey, I'm going to pass you this, but please don't change it because there's another object currently sharing it. So it'd be really good if you just didn't call any of the modifiers. Thanks, bye. Comments are not perhaps the best way to guarantee these invariants in your code. So I treat that as a separate issue, but it's a problem that you need to create if you want to solve it, rather than people, oh, I'm not going to do it because I might have a problem. No, you already have a problem. Okay. So we can have this simple idea. Remove modifiers is the simplest, but how do we actually replace our modifiers? Replace modifications with constructors, so construct new objects, move modifiers to a builder kind of style, replace the side effect with a new object, make void methods fluent. So there's a kind of a series of things that we can see in moving from one style to another. Now, I want to talk about objects and psychoanalysis. It turns out psychoanalysts are utterly obsessed with objects. Slightly different objects, but I think it's kind of nice. That's a stack of psychotherapy books. My mother was a psychotherapist, and it has had no effect on me whatsoever. Yeah, do not trust me, as software developers, your kids will grow up way less screwed up. However, it did give me an introduction to objects from a very early age. And a book is simply a container of an idea like a bottle. What is inside the book is what matters. We will see that the content is there. However, the reason I've got a book there is the gratuitous fact that it is, in fact, a stack of books, which means that I am going to talk about stacks, that quintessential lab rat of computer science. I'm going to shift language here. I'm going to shift to Java because I was told, guess what, NDC is broadening out from the .NET world. So here you go. And it looks no different at this level. But no matter. If you ever struggle with porting between the two, there are a few differences, but mostly it's case. Change main, the case of main. So if you know where the case shift is on in your IDE, you're sorted. That might be a little flippant, but it's a good starting point. Okay, so let's actually put some stuff in that is Java. So I've got a structure. I've got a number of things I can do with it. I'm going to keep the objects API very simple. You've got the depth. I can query the depth. I can ask for the top element. Pop is what we might call a pure pop. In other words, it does not return a value. It just pops. It is a pure imperative operation in that sense. Kind of curious to hear the words pure and imperative in the same sentence there, but there is the idea of this is a procedure in a classic sense. It does not return a value. It merely changes the state. And then we've got push. It's 4 operations. I've wrapped an array list on the inside, and this does expected things. If you try and pop or take the top of an empty stack, you get an illegal state exception. Okay, now, to make this immutable, there might be an initial sense where you might go, oh, right, so I need to create new copies of, every time I do something to a stack, I need to create a new copy of the stack. This is going to be quite expensive, to copy a collection every single time you're going to use it. It was okay to create a new money object, a new time of day object, or whatever, because these, actually, it's not going to make much difference. We will end up with similar amounts of object creation, but we're not talking big objects here. Collections have a very different role. We're actually talking at the collection level. And whilst this is a toy example and the number of books in the background is relatively small, when you start dealing with collections of millions of items and somebody says, yeah, I'm going to add an item, I'm going to push an item onto that, so let's create a copy of it, all million items, and then add one, that's clearly going to be an expensive way of going about stuff. And it's not merely a case of don't worry, the memory on your machine will catch up eventually. We've actually created a problem here. So a problem which we can respond to using persistent data structures. In computing, a persistent data structure is the data structure that always preserves the previous version of itself when it is modified. Again, I refer you to version control systems. The reason I'm making that point is because I had this experience a few months ago. I ran a workshop for one company, and I talked about persistent data structures, and I introduced how to implement them. And one guy said, OK, I get all this. This looks really cool, but I can't see how I'm going to use it in my day-to-day job. And I said, do you use Git? And he said, yes. And I said, you use it in your day-to-day job. OK? This idea of retaining the previous version, it doesn't actually have to be immutable. Let's be very clear. When all of software development is ultimately about maintaining a series of clever illusions. When people say that executing a pure function has no side effect, that is an illusion. Of course it has a side effect. You can actually sit there and measure the amount of electricity used. You've changed the entropy of the universe. I think that's a major side effect. Okay? So if you're a Haskell programmer, you'll think you're not changing the universe in the way that you intended, for good and whatever. You are changing the universe. It is a measurable effect, but that turns out to be not the effect we're focused on in the code. So as long as we maintain an illusion, then that's what it's about. That is ultimately what any optimization is about. It's about maintaining an illusion of something else, but doing it in a different way. So what we need, such data structures are effectively immutable, as their operations do not visibly update the structure in place, but instead yield a new updated structure. We will make it look as if we have lots of fresh new stacks in memory, but actually that's just an illusion. Don't confuse this with the idea of persistence in sense of data storage, however. Okay, so let's look at everybody's favorite default data structure, the array. And I'm not going to go far into persistent data structures. That is really a topic that for which there is an awful lot of very interesting research, but let's start with the simple stuff. An array. So an array, referred to as A. Okay, that's how am I going to make this, if I make this a stack, so I've got a stack of 4 items. Okay, how do I pop from it? Well, that's easy. First of all, I'm going to say B is equal to A, so we're now pointing at the same stack. Then I'm going to go, okay, B is A dot pop. At this point, I've now got A referring to a stack of, I've got A referring to a stack of 4 items, and I've got C referring to a stack of 3 items, which happen to be the same as the ones that A is referring to, but that doesn't matter. It's an illusion. We haven't actually had to copy this stuff. And this is great. It doesn't work for push, though. So let's shift that to a linked structure, at which point we can recover this. Okay, A, B is A, C is A dot pop. We move through, and then the clever bit, which is where we do push. Okay. And we can have this snaking off into memory. I can quite happily say E is the push of a different value there, and we end up with a tree going off into that. So we've got a shared data structure. If you try and do this in systems without garbage collection, good luck to you. It's non-trivial. It's a bit of a pain, to be precise. But what we've done there is maintained an illusion. As far as we are concerned, if you look at those 3 roots, A, D, and E, we've got 3 stacks up there. But you're only seeing one data structure that's linked. We've got 3 stacks up there. There is A, which has 4 elements. There is D, which has 5 elements, the top of which is X, and the other 4 are identical to A. There's E, which has 5 elements, the top of which is Y, and the other 4 are identical to those in A. So that is the essence, if you like, of a persistent data structure. However, to maintain this illusion, there are some rules. There are some house rules. And we also recognize this is not a new idea. I mentioned 1950s. What I was really referring to was Lisp, which is kind of similar age to Fortran, although the first proper implementations didn't come about till the early 60s. But it was all there. This is a very, very old idea, and that is the essence of the illusion that Lisp offers people. So we can go back to our stack, and we can offer a very different worldview on it. Instead of thinking of a stack as being a thing that you change, it's a thing that you've got to ask questions of. So we're going to change, there we go, we've got depth, top, no difference there. Pop is now, I'm not going to pop a thing, I'm going to basically say, given what you are, what would you be without your top element? Yeah? With pop, or without top. Yeah? What would you be with this extra top element? So it becomes a much more serious, a much more polite conversation based on leading questions, admittedly. So we have a very different way of looking at this. Because things never change, what I'm going to do here is I'm going to recognize that the stack has a very simple state model. And it turns out that all empty stacks are equivalent. And I can actually describe a behavior for them. So I'm actually going to implement the interface. I'm going to say, empty, I have a class for empty stacks. And there we go. The depth is always 0. The top, it doesn't have one, so it always throws illegal state exception. Pop, it always throws illegal state exception. And when I come to push something, it returns a non-empty stack. I'll factor out a few things here just to keep the slides a bit tidier. So we've got that, and then when it comes to the non-empty version, then the depth is always 1 plus the depth of whatever it was. If you're concerned that this leads to a linear cost, you can also cache the length, because it will never change. That's the benefit here. And the top is always the top. There's never an if, and so on. So it turns out this is surprisingly simple. Stacks can be empty or non-empty. The behavior for empty is always the same. The behavior for non-empty is always the same. And what we've done is we've eliminated if statements. Indeed, there is indeed a thing called the anti-if campaign. Absolutely. Slightly tongue-in-cheek, but nonetheless, puts in an important point. The goal of the anti-if campaign is to raise awareness of the effective use of software design principles and practices by first of all removing bad, dangerous ifs, which is all of them. Branching code confuses people. Yeah, we are merely mortal, and we are human. We struggle with ands and ors and ifs and elses. These are where bugs come home to roost. So the difference in usage between our 2 different stack models is previously we said we've got a stack, now I'm going to push something on it, now I'm going to change it again. Here what we do is we say, well, I'm going to start with an empty stack, and then what I want is the stack that results from empty having NDC pushed onto it, having London pushed onto it. So if you like, there's a much more obvious data flow going on in this. We've replaced a sort of like then do this, then do this, then do this with a flow of possibilities, a stream of changes or a stream of application. Now, for this to work, there is an illusion we must maintain. The type that you put in there, so string works nicely, must be a type that is immutable, or you must guarantee that only instances that will never be changed there. Because we have a shared data structure, if you put inside that collection objects that can be changed, you will break that illusion. Now, you're already doing this without realizing it, particularly if you're using things like mapped or dictionary collections, because you're always told, if you look at the small print, please don't change the key. You're not allowed to, please don't change this value, because you will actually blow the encapsulation of the data structure apart. Because if a data structure is carefully, either by hash code or by sort position, put a value in a particular location, and you change via a different route, via a reference to it, its hash code or its sort position, it will never find it. You've actually undermined the encapsulation of another object. So there's normally a polite warning, but that is enforcement by comment, or enforcement by MSDN, which is not really worth the paper it's printed on. So here we have this idea of replace mutable collections with persistent collections, either an actual persistent collection or using something in a persistent manner. Replace mutable collection values with immutable values, make sure the contents are unchanged, we kind of dealt with that before, and replace state-based object behavior with polymorphism, because they never change. Now, the final bit that I want to cover is this question of control flow. So there's a really nice example in 97 Things Every Programmer Should Know from Berk Hafnagel. Put the mouse down and step away from the keyboard. Now, this is just generally good advice. Okay? If you are struggling with a problem, you think that the challenge is to solve it. Okay? That's kind of obvious. Yeah? I have a problem, I should solve it. And what you will do is you will dig. You will dig into it, and you will dig further. What you will ultimately achieve, if you've not solved it, is a very big hole. You will find yourself at the bottom of it. It turns out that it's very difficult to solve certain kinds of problem at the level at which you found them. You need to do something different. So the advice here is put the mouse down, step away from the keyboard, and he uses a particular example to motivate this. I have a different way of looking at it. I've always recommended that people do something that changes the situation they're in. You need to think differently. If you are stuck in something and you are thinking the same way, then that is your problem. So I often tell people, if you've been mainlining coffee all morning and you have a problem and you're just filling yourself with more coffee to solve it, then I've got a radical suggestion for you. Try some chamomile tea. Because clearly coffee is not the answer in this case. If you're sitting there virtuously saying, well, hell, I don't drink caffeine, I drink chamomile tea, then my recommendation to you is drink some caffeine. Because the thing that you're doing, you need to change. You need to think differently. And trust me, if you don't drink caffeine, drinking caffeine will change your behavior. If you are sitting down, stand up. Yeah, it's this kind of thing. Go home, go for a walk. Yeah, whatever it is. Go and look at pictures of cats, unless you do that all the time. Okay, so the point here, and he gives a specific example. He said he was wrestling with this code, and you look at it and it's very procedural. Okay, we've got a string. We're going to parse it as an integer. If that fails, then clearly the thing was not in an integer format. And there's a ... here, which is operative. In other words, this is quite long code. And this is kind of brute force its way in. Now, if you're writing enterprise code, this is what you do for a living, okay? But if you want to do something different, then put the mouse down and step away from the keyboard. Which he did, and he came back the next day and said, oh, what am I doing? I recognize this is a different problem. It's like there's a regular expression that does this. Now, there is always the standard joke, I had a problem, I solved it with regular expressions, now I have two problems, which I always think shows a lack of appreciation for regular expressions. I now have star problems, On the other hand, this goes right back to what we're doing here is we are replacing a very explicit decision structure with something that is far more intelligent. We are using an intelligent data structure. And I look at this, and again, I use my kids as sort of a simple way of thinking. How would I explain this to my kids? It's as bad as trying to explain public class, blah, blah, public static void main. I've taught them Python. It's a lot easier. This is just like putting needles in your eyes, but without the fun. So the point here is I can explain the time format very easily to somebody who is not a developer in comparison to this. This is a painful way of walking through this. This, I can say, you might not be familiar with the notation, but let me show you what's going on. Yeah? The one thing it doesn't, I did actually get a bug report for this in the book. It said it doesn't account for leap seconds. And I said, if you can properly account for leap seconds, then file a bug report. Because I've met very few people, one of them's in the front row, who know enough about leap seconds to be able to file an accurate bug report. So let us just work with something we know works most of the time. So I'm going to close with a different example. And so I want to talk about this idea of moving away from the explicitness of code that we become comfortable with the idea. After many years, we become comfortable with the idea that we have become program counters, which I think is particularly demeaning from a human point of view. You're very good at going through code and going if and while and structuring it all together. There is this idea that perhaps we don't need to spell out every single loop and decision, but I'm going to focus on loops for the moment. We don't need to spell out every loop. You have written all the loops you will ever need to write in your life. In fact, you've written more than them. You know the kind of loops that I mean. You know, the one that goes through everything and does the same thing to everything in a collection. And then there's the accumulation loop. And then there's the loop that does something on a condition. And then there's you've got this all in your head. It's all lovely and, it doesn't take much programming experience. And then you probably encountered all the kinds of loop that you will ever need. And yet, you have to repeat them. Yeah? There's something profound and self-referential in the repetition of writing a loop. And perhaps there's something calming and kind of like there's a sort of a yogic feeling to it. And it's a mantra that you chant every time you're trying to get some work done by avoiding the work and writing a loop instead. That somebody will then have to come along and interpret, because the loop is all about bookkeeping. It's all about, I'm going to set up this for it, I'm going to do this, I'm going to do this, and this. And somewhere inside it is what you're actually trying to do. So we see that there is a trend in many languages that did not start there to embrace forms that look like this. So Java's ended up with a collection pipelines model. C# has ended up with LINQ, embodying a more sort of predicate logic type thing. And whichever way, that's the direction that this is heading. And so Rebel Labs published this beginning of last year, I think. No, the year before. And they had an example here. Now, I looked at the example. It's the one in the middle, first stream example. I looked at the example, and I thought, that's wrong. They've implemented it incorrectly. So I tweeted this at them, and they corrected it, which is still wrong. So I don't think it's correcting it. It's incorrecting it. They took a wrong thing and made it also wrong, but differently wrong. OK, I'm not expecting you to understand what's wrong there, so let's build this back a little bit. So what we've got is their objective. Get the unique surnames in uppercase of the first 15 book authors that are 50 years old or older. OK, so we take a library, which is some kind of collection of books. We stream it. We map. We take a book. We get the author. We filter in, select would be a far better word. We filter in. We look at the author. We get their age. If they are 50 or over, we're having them. And then we limit that to 15. Then we get the surname. We shift it to uppercase. We uniquify it. And we collect it to a list. That's brilliant, but unfortunately, it doesn't actually meet the spec. Why not? OK, because I have multiple books by the same author. So if my first 15 books, for example, are by the same author, then I haven't actually got the first 15 book authors. That's not the same thing. So OK, let's try this one again. So this is their correction or incorrection. What they do, we get over 50, get the surname, shift it to uppercase, uniquify it, limit to 15. Unfortunately, that is the first 15 unique author names, which is not the same. You may have authors that have the same surname but are actually different. So again, this fails. And actually, it turns out you need to uniquify in two different places. Get all the authors that are over, that are 50 or over, get the unique authors, limit that to 15. Now, do your case shifting and all the rest of it. And that actually matches their requirements. So what is interesting here is, again, if you're not familiar with this API, you can actually walk through it and understand it with the level of explanation I've just offered you. So I did this example a couple of years back, and Trisha G mentioned to me, she said, you know, that's really good. But wouldn't it be more interesting if you showed what the original control flow looked like? That would be compelling. You know what? She's right. So I did that. So this is the original example. As you can see, it goes on off the screen. So let's just shift the... So first thing, more code. Next thing, how much of that code is actually about what... Can you see that it is... One, can you see what it's doing? Two, can you see that it's wrong? You've got an awful lot more things to do. Of course, you're intelligent. You're not going to admit this is harder. I am a programmer. I'm at NDC. Of course I'm smart enough to do this. I'm not questioning your intelligence. I'm questioning the immediacy of this. And we should move away from the idea of, hey, it was hard to write, so it should be hard to read. We should move away from that philosophy. And the point here is that, yeah, that's not as immediate. I'm having to do all of that. Yeah, OK, remember that piece of state. This is an accumulate. Do this. This is the incorrected example that they put up. And this is the correct one. None of them looks more or less correct or is easier or harder to read than any of the others. But when you compare it to the pipeline version, the data flow-centric version, then there's a difference. So one of the great pieces of advice given by the author Elmer Leonard is try to leave out the part that readers tend to skip. Okay? This is good for life as a guideline, you know, documentation, whatever. Cut things down. And most of what we write is mechanical background noise. We can refactor it away either by using existing libraries or by learning to do the same thing ourselves. Hey, there's a loop there. I keep repeating it. Why didn't I factor that into a method that does that for me? And there are a number of different approaches that we can take. So what I want to end with here is this very simple observation that we've got a set of our motivation here is we're not trying to make things immutable because people said it's good to be immutable. We're trying to make things immutable so we can understand it and we can change it more easily. It goes right back to what John Carmack was saying about the struggle that we have understanding the states that our code can be in. By definition, a system that is a legacy system has these problems. And so therefore, how do we dig ourselves out of that particular hole? Is there a nice, simple set of transformations that get us to a thinkable, reasonable model? And it turns out there are. I have not covered everything. I've not talked about larger architectural changes. But what we've done is we've already targeted some of the noise and some of the very common cases in the code and started moving code in a direction to the point where we might actually say that's an emergent style of the code system. If we recognize that many coding practices and coding issues are actually social, there's those forces that people go on. If that becomes the normal way of doing things, eventually people start questioning the bigger picture. How do we make this more of a data flow architecture? How do we separate things so that their state is more isolated? We can minimize moving parts. We can hide moving parts. How do we do that? But it starts with the little stuff, the very simple habits that we have. And so I'll end with a quote from Lucius Carey, which is relevant given that we are across from the Houses of Parliament. Outside the Houses of Parliament is a statue of Oliver Cromwell, who was responsible for, well, Lucius Carey was on the wrong side of the English Civil War, but he did leave us with a good quote, which is, you know, all that matters a few hundred years after the event. When it is not necessary to change, it is necessary not to change. And we should actually seek that in our object models and our type systems. Thank you very much.